Welcome to the last session of today's LISA conference, and after this you have the plenary session after this, and hope you guys get to go home on time without any problems. So this is where the slides are. Actually, first let me introduce myself. I am Mohit. I am on the Bing and Cortana engineering team. I'm going to talk to you about debugging at scale. In a sense, LISA this time has been death by debugging for me. In the sense that, in a positive sense, there's been a lot of talks on debugging and various aspects, so which is a good sign. But I hope you guys are not all bored by it by now, because I'm going to finish it off really well. So this is where you'll find my slides. I'll get the QR code later as well for you guys to look at later on. So how many of you can recognize this image? Okay, not a whole lot of them, but yes, absolutely quite a few. So this is, there's a bunch of stories going around. I will take the story that is on Wikipedia. Admiral Grace Hopper, people feeling familiar with her? Yes. If there's one person, you need to look back who went to computer science and did a good job of making sure everybody was comfortable with it, it was her. So Admiral Grace Hopper asked her team to document the first physical bug that they encountered in their Mark II computer. And this is probably the first instance that they had to debug. Now, there are stories around, when that happened and who did it first. Probably Thomas Edison did it in 1878. But from our point of view, she was the one who brought it to mainstream engineering, and we took it from there. Interestingly, yesterday when I was reviewing the slides, I noticed something. If you notice the timestamps, the first timestamp, 1525, says started multi-adder test, and 1545, it says found a bug. 20 minutes it took them probably to find a physical bug. And I was curious, like, what kind of a computer was this? And it was a Mark II computer with 13,000 relays. And they were able to figure it out that it was on relay number 70, panel F, whatever, within 20 minutes. Those are some goddamn good debuggers right there. And I wish I had that power to do it myself. Anyway, I'll go into some philosophy. Dual nature of debugging is what I call it. And when I think of it, the way we develop code, debugging is a paradigm that's available throughout our segment of how we do things in life for software. And developers treat it in a different way, and SREs treat it in a different way altogether. After our product ships, it is on SREs to make sure that debugging is done. However, the pressure changes a lot. When you are developing code, the pressure is slightly lower because you're not seeing the results immediately. But on the other side, customer experience is critical. So SREs, feel that pressure quite a bit. And as a result of this pressure, the speed also changes quite a bit. And when I say the speed, the desire to come up with a quicker outcome from a debugging solution is faster for SREs. Developers can do a whole different thing altogether. Which brings us to the point, debugging is hard. If it was easy, I was not going to be here. Debugging is hard, and I'll let this comic strip from SKCD, say for itself. Hopefully you guys have seen it. If not, 5 seconds to read it, quick. When I read it, I did not know who the hell Martin the Warrior was, and I went into a whole different tangent altogether, and I realized I am living the comic again, because I was on a Wikipedia page that led me to another Wikipedia page to another one. So that was an interesting way of doing things. So debugging is hard because of two reasons. Number one, who am I? And it's not an existential crisis question about who am I as a human, bad person, good person, or such. The question is, who am I when I am trying to debug? I mean, when I think of it, I think I'm goddamn Sherlock Holmes. I want to get to the bottom of the problem and figure out what the hell's going on. Like, should I be Sherlock Holmes while I'm debugging, or should I be somebody else, right? And to tell you the truth, most of us, I believe, are explorers. How many of you have tried to understand how complex systems work when you were a kid or a teenager, like took something apart, hoping everybody, because otherwise you're not an engineer, right? So I did that. However, it is a good thing to have, but at some point in time, you have to realize that we should learn. Doctors are of two kinds. Doctors are the same. There are doctors who treat you outside, and there's doctors who treat you at ER. So ER doctors have a very specific goal. Stop the blood, right? Get you back into stable condition, and then go back to the next patient. They are doctors, but they know what they have to do. They are wearing a different hat. As SREs, we need to remember that while explorers are a good thing, being explorers, it gives us the right context. Getting to wear that hat as an ER doctor is extremely critical. The second problem in my mind in terms of debugging is broken tools. And when I say broken, not really broken in the general, but they have lost their context in a highly scaled out environment. And where everything at scale, you need debugging at scale, deployment at scale, networking at scale, things don't scale, and debugging tools don't either. So we need to fix them. When I got this image, I realized that this is probably a real poster from the Second World War era, 1942 to 1945. I believe the National Archive has this because they put it because the factories were actually having issues with their tools. So they had to advertise. Interesting story behind that. So what do we do? What are our traditional tools? Debugger is what we have already known for. Memory profilers and physical logs. These are our traditional tools, and not obsolete completely, but again, like I said, they don't work in a scaled out environment. There's a fourth tool that is missing here, and if you are an SRE worth your salt, you would know the fourth category. Can somebody think about it? Packets don't lie. Wireshark, a network packet capture tool, right? I mean, I would not be able to survive without one, because at the end of the day, packets don't lie is what I think, and the fourth one is the missing tool over here. In short, traditional tools that don't scale, and the main reasons are the distributed nature of our systems, and the second is, especially in our case, is the high amount of traffic that comes in. It simply doesn't matter. Like, even if you had a single MOX, theoretically, with such a high amount of QPS or requests per second coming in, there is no way we could imagine what we could do. So what do we do from here? The solution is we take some principles and put them to work. And I say some because there are like 6 or 7 in my list. I have them in the addendum on the deck, but I'll only talk about 3, lack of time and such. So number 1, error messages are still useful for users and engineers. And when I say error messages, I mean the error messages that users see on their basic pages and not the error messages that you see on the logs. And you might think that's antithetical to scaling, right? Does it make sense? Like, why am I talking about individual error messages? And the reality is, most of the time your telemetry and systems will be able to capture a problem and record and alert and so on and so forth. At some point in time, you will be called up by a customer seeing a problem, and you'll be like, I don't see it on my systems. Where is it? And at that point in time, these error messages don't help. What helps are error messages like these, right? The one on the right is us. There's some reference IDs and such over there that tell you and give you a breadcrumb that you can follow with. The one on the left is also an error message. Can somebody take a guess as to which error message, which site has that error message like that? Nothing to do with Bing or Microsoft. Hint. YouTube. So YouTube had that error message. So error messages like these are good. They tell you where to begin. They give you a breadcrumb that can lead you to a distributed way of solving a problem, but it tells you where to begin. So never underestimate things like these. Rorschach test for you. What do you see when you see that animal there with that thingy there? Sad panda, right? So it's a sad panda, and apparently the ice cream has fallen out of his hands, and so he's crying about it. When I saw it first in my team, I said, that doesn't look like an ice cream to me. It looks like he puked, and that's why he's sad. Now you will never be able to unsee it. Principle number 2 that I have is distributed tracing is the new debugger. A lot of talk on distributed tracing. I believe everybody knows it. The image on the left is interesting because I've always thought about what is a physical representation of distributed tracing. And the one on the left that you see is basically a picture that shows an exercise going on in Camp Pendleton, a military exercise, and they're using tracer bullets to shoot at a particular target. And what you see is in physical manifestation, when a picture is taken for a tracing system, this is what it looks like. And I can pretty much guarantee if you made an electronic version of your own software, it would look like the same image itself. So, I mean, what I mean to say is distributed tracing works. You just have to put it into action. So this is what we did. Our challenge in distributed tracing was twofold. One was the number of components that we have within search, literally thousands, tens of thousands of plugins and components. So if we decided to put distributed tracing, it would take a long time. That we started 4 or 5 years ago. Everything was put in place. And then the problem was scale out, which is tens of thousands of machines, and how do you make that happen? So we came up with our own system at that time. It was called Stamp Manager. It's a snapshot over there. The one on the right is Zipkin, which is, in my mind, the right choice these days to make distributed tracing successful in your products. It may not run by itself. You need a lot of scaffolding around it to make it compatible with your internal systems, but that is the right way to go. What it does is it allows us to look at various components in real time, to look at the traffic flow, and there are multiple components in general, like speller, geocode, location detection, market detection. All of those components can flow through a distributed tracing system. I will not go deeper into it. The slides I've left because we've already covered that in previous 2 talks. The other one is the buzzword of the century, machine learning, apply machine learning. Like, if you have this in your talk, you're probably going to get selected in LISA anyway, which is why I guess I came here. But anyway, I feel that this is the buzzword. Most of us don't even realize that we probably might be using machine learning, but because of the complex nature of the word, we just feel that we are not. And if I used artificial intelligence, you might be even more scared. Like, at the end of the day, the terminology that we use as engineers, as SREs, isn't academic enough to be at the same level. And the first question that you might ask is, what does machine learning really do? And Randall Monroe put this comic strip really aptly, and it describes machine learning in the best possible manner. Right? It's just a pile of linear algebra that you keep, mixing, and then you keep tasting. If the soup looks good and tastes good, this is the recipe that you will use forever in your life. And frankly, that is what machine learning is. You keep tweaking variables and activation functions and whatever that might be, and then when you come up with the right model, you keep that model in your larder and say, every single time a new log entry comes in, I'm going to use the same thing and put it into practice. Why don't I show you our pile of linear algebra? Again, this is academic terminology. A lot of big words maybe, I don't know. There's a lot of things that you can do within machine learning that are relevant to debugging in general. And we will go through some of them for lack of time and to make sure that everybody does not go back to sleep. David did a good job of waking you up. So first is log relevant tokenization. We talked about it. I believe there was a talk yesterday on a tool called LogMine. It did this magical thing of taking heterogeneous logs, automatically detecting key value pairs and extracting them for you. That is basically what tokenizing does in a general sense. What we do in addition, in a way, or in a different way, is we extract sentences out of our logs, and sentences by word, like if anything is longer than 3 words, we take it out. I'll tell you why later. Then we also auto-detect keys, as in when you have key value pairs, A:B, A=B, we try to take any keys with, for example, words like latency, timeout, time, failure, and such, etc., and classify them in a different way, and proactively extract them and bucket them separately. Again, why? I will tell you later. It's just a story. Key value pair identification. Core to sentence extraction, log tokenization. The reason is then you can do other kinds of analysis on all key value pairs and see what's rising, what's not, when you have millions of log entries. The second is classifiers, and this is where sentences come in. When you have development teams spanning across the globe where English is not the first language and driving the right standards is it's not possible for writing error messages, we came up with this where we said what we do is we look at all the sentences that were extracted, run a classifier on it, and figure out what are the negative sounding phrases in logs. And any negative sounding phrase, a spike in a negative sounding phrase is a problem. Unless it's a query itself, which is a separate red herring we had at some point in time. Like Michael Jackson died, so spike up, something like that. Anyway, so the examples that I have are name not resolved, took too long to respond, and unable to reach. They are negative, so the graph that you see is a real-life example of the same kinds of errors. The system that we built is called Flycatcher. It's able to detect negative phrases, within 5 minutes of a bunch of problems happening, we are able to see this kind of a spike, and we can correlate that with whatever's going on in our system. This is different than exceptions, by the way. Sometimes you may not see exceptions clearly. It's just that something is taking too long. It is not an exception yet. So that is how negative phrases really help. Clustering. Clustering is, in layman's terms, putting things of a similar kind in a separate bucket and trying to see exactly how they form together. Clustering really helps when you have different key value pairs and see how they come up. This is an example of a debug graph that we call. Given a bunch of queries of the similar nature, say if somebody were searching for cats, this is what cats look like usually. This is what is happening with the query called cats. And then we can figure out where that problem might be happening. So clustering allows us to look at that. Now comes that connotation about, I talked about keeping latency kind of key value pairs separate. And the way it helps is, in most of the systems, sometimes timeouts are the reason things happen. And when timeouts happen, things happen at a square wave. You hit 500 milliseconds and your system just times out and does something funky with it. What we realized was clustering on a floating point number scale also tends to help, because we noticed when errors were happening, timeouts were of a certain 10,000th plugin were at 250 milliseconds. And we noticed that a large chunk of queries were timing out, and all of these happen to have 250 milliseconds weird latency at the same time. That is not right. So what we realized was, even using real numbers for clusters, especially for latency and timeout, can really help quite a bit. Anomaly detection as a platform. So if you don't take away anything else from this talk, the only thing I would urge you to do is think about anomaly detection horizontally for every single software system that you have. And anomalies is a generic word. Yes, anomaly is a problem or something that you don't see often, and so on and so forth. Two kinds of anomalies I think of. One is very important, time series data. You should be able to take an API, throw time series data at it. It should be able to churn out anomalies and say time data X, Y, and Z seem to be odd given the amount of data you have. And the reason this becomes extremely critical is because alert thresholds, arbitrary values don't scale. Each system has its own way of measuring itself. There is no way you can continue to keep updating your alerting systems, because false alarms increase. False alarms go up, and then you're like, oh, I forgot to set up the timeout for that to a different level altogether. Or a default timeout for this alert was not the right one. This system operates at a different layer altogether. Anomaly detection for time series data, absolute must-have. Another kind of anomaly that we see are infrastructure-based anomalies or key value pair-based anomalies. And if suddenly in the last 10 minutes some oddity started creeping up, a particular pod or a particular machine, a particular network switch happens to be in the way of all the failing queries, this system is extremely useful to pan that out. So after the extraction happens, after classifier works on it, we put the data into an anomaly detection system. It notes it down, and you can guess this is Kibana. On the right-hand side, we do machine learning on our own. But the reason I showed it on the right-hand side is, even if you don't want to do anomaly detection on your own, systems like ES allow you to do anomaly detection. What we do is we use Twitter's R library, open source. We modified that for our purpose, and it works really well. We plug it in, and anomaly detection for time series data works really well. So again, every error page is analyzed in almost real time, and outliers are detected. Crashes are also detected. We can find out outliers in services, and then we can figure out a particular rollout or a particular patch might have triggered something bad. Bringing it all together. So this slide I put in yesterday and today morning, and the only reason I did it was because we talk about so many different things. I wanted to walk through how everything comes together. User events happen on the left-hand side. We have an Apache Storm Kafka pipeline that runs to grab all user impressions, figure out where errors are happening. And the reason is we ensure that by the time the last byte leaves our data center towards the user, we should already know what we sent to him. If we sent a bad response, we should know about it before the user did, right? So we take that, pump it into our Kafka systems, stamp manager, that distributed tracing platform we have, picks it up, throws it out to tens of thousands of machines, picks up 1,000 logs, sends it to this flycatcher system. It does analysis, outlier detection, anomaly detection, punches all the data into Elasticsearch so that it can work on it again later if needed, and then throws it out to Kibana for display to the dashboard and to an engineer to look at. One critical thing is, when you think about automation, the first question I usually ask is, why is a human even involved over here? Like, why do I need an engineer? And it's a very nuanced thing. This is debugging. Debugging forever will require engineers to be in the midst of things. It will not be automated. Otherwise, it becomes auto-mitigation, right? So debugging will generally require a human touch to it. And what happens is, when an engineer gets woken up, he looks at an alert which says error rates per second increase on data center ABC, whatever it is. He wakes up at 2 o'clock in the morning, opens up his laptop, tries to log in. 5 minutes have passed by. By that time, 60 seconds and 5 minutes for everything to go on. He will have a dashboard ready, customized for this incident call that happened, and shows you whether there were any machines, network switches, data centers, outliers of any form that can, or even experiments. We run experiments all the time. We are always afraid experiments cause more havoc than anything else. So all these things are already either ruled out or ruled in by the time a person comes on his desk at 2 a.m. So that really helps close the time to detect and time to mitigate for us quite a bit. So that was all about bringing it all together. One thing I did not see much about generally in the talks is privacy. And you could ask, like, what does privacy have to do at scale? Privacy on a single machine is the same as privacy on a bunch of machines. But in our experience, it is not the case, especially in debugging. And you see that URL over there. I wanted to paste a Dilbert comic, but I had to buy it. I tried to buy it. They wanted me to call up some number to buy the comic strip. I did not want to do that in this world. So I would urge you to look at that and figure it out. But I'll give you the story. Dilbert dies, and Mr. Garbage Man, if you remember from the Dilbert comics, comes out and fixes a cloning device from his garbage and revives Dilbert back. And Catbert, the cat, the evil cat, surprised, says, "You were able to reconstruct Dilbert from his garbage?" And then he says something funky around it. Like, the point that hit me was the comics have showed that you could build a person back from garbage. And in my mind, logs are garbage in a lot of extent. Like, we treat it like smoke, or like that comes out after an engine is burned off, right? Smoke can tell us a bunch of things, but maybe, bad analogy, I don't know. My point is, we did not pay enough attention to logs. We think we might have removed data, but sometimes when you have 1 million requests, 10 million requests, and billions of logs of like that kind, the latent power of aggregated logs comes alive. You will be surprised at what machine learning can do and find out, even with seemingly anonymized logs. And you need to be very careful with it, because I don't know how many about your companies, but if you ever are a global company and you are operating in Europe, next year is going to be interesting. How many of you know about GDPR? Not enough in my mind, but if you're US based, it's okay. If you're not, Google or Bing, whatever you want to do, GDPR. GDPR is going to be very critical, because you're going to have to figure out when somebody says they have a right to be forgotten, how do you forget people, not even from the databases and online systems, but from the logs as well. All right? Otherwise, it's 4% revenue loss, or whatever that is, fine. So it is very critical. Debugging is not taken as seriously for privacy. It is extremely important. Need to work on it. I'm spending quite a bit of time. Exposure to third-party analysis and hosting. That is another thing. We tend to keep our clouds data on cloud and use third-party systems to munge it and try to get analysis. It is something to be aware of, that you make sure you keep your data appropriately and you have right expiration notices on all your data, especially for debugging, because those are the last things that people look at. Because debugging only happens when there is a problem, right? If your system is chugging along perfectly fine, nobody looks at it. So my recommendation is to make sure you keep a close watch on what's happening. Some closing thoughts. First, distributed tracing, no-brainer. Absolutely. It is a difficult thing to implement. Like David said, demolition. Whatever you have right now, build it up with distributed tracing. Need to make sure that it's in place so that systems can scale out and debugging becomes easier. Machine learning delivers, really. I mean, I was not a fan of putting it, I was irritated by the word machine learning all the time, but I used to do clustering, but then I realized, yeah, clustering is machine learning. It's not a buzzword anymore if you use it the right way. So try to delve into it. Anomaly detection, absolutely do it. It'll benefit not just your metrics, log analysis, but your business as well. I feel that we do not appreciate anomaly detection for our business side of things. If you put it in place as a platform, you will be able to give a lot more out to people. Privacy matters, extremely important, especially for Europe now. And obviously, debugging is fun. I never meant to say that you're doing it wrong, but we just need to take a different mindset. And you should always keep your Sherlock Holmes inside you alive, because that is what makes us good engineers, and that is what is going to make you aces at debugging. So that is all I had. If you had any questions, let me know. I think I have about 4 minutes.
Yes, and if you have any questions, please go forward to the microphone because we're broadcasting.
There are questions.
One of the most stunning things that happened to me here at LISA was the talk earlier today about what if you're not LinkedIn, Microsoft, Facebook, Google. Of the best sort of high-level review you just gave, if I'm a small shop and I can afford to do one of those badly, what should I start with?
Anomaly detection. Absolutely.
Thank you. Excellent talk, by the way. Thank you.
Thanks.
I mean, you also mentioned that you reused Twitter's API for something. Could you tell us a bit more about that?
So there's a Twitter R library for anomaly detection. They published it, I think, 3 years ago or 4 years ago. I started playing with it when I was looking at some reachability data. So it's based on R. So a lot of our work I did was in R itself. So I got a good idea. So all my offline systems run on Twitter's R library. Then we have our own systems in Azure. But yes, if you wanted to start somewhere and it did not appear to be Elasticsearch machine learning, you could play around with Twitter's R library to see what it does for you. You just need to give it time series data for a week, and you'll see what happens.
Hey, I'm super excited that you're using machine learning in SRE type stuff, because I think it's something that all of us are probably going to start doing a lot more of. Question, you were saying that you do this anomaly detection and you have this machine that's acting up, but you still wake up an engineer? Like, why don't you just shoot the bad machine in the head and
absolutely.
Let the engineer sleep?
I should put it this way. The time when an engineer gets woken up is when the problem has not mitigated itself, right? Most of the times, a single machine, like almost all of the times, which is why 1% always happens, 99% of the times, a machine's watchdog system should be able to see the problem itself, and it shuts it down. That anomaly part comes after the fact. Like, say next morning somebody looks at it and says, what happened? There was a spike, and very short-lived spike. We see, a single machine, but nobody got woken up because within 5 minutes the machine was out of rotation. And there are multiple, like tens of machines that take parallel load, so no user got a bad response. Otherwise somebody would have been woken up, because we have to work at 4 nines. So that means any 10 errors would cause, or 100 errors would cause things to start triggering somewhere. So yeah, machines don't, but if they do, this really works. And not just in errors, even in higher latency. These machines are showing 10-second latency. That's where it's more useful.
So that's it for the questions. Thanks one more time for Mohit Suley.
Thank you.
And the next session is at 4 o'clock.